In this video, we're going to explore the idea of stationary waves. And I'm going to use an online graphing calculator called Desmos to help me. First of all, let's enter a general wave equation. So this is the general wave equation. Y1 is the displacement. A1 is the maximum displacement, that's the amplitude. The cosine function can go from +1 to -1. So you can see that y1, the maximum value it can take, is a1, which is the definition of amplitude. I've used a w here, but actually I wanted to put an omega. Omega 1 is the angular frequency of the wave. That's equal to 2 pi f, where f is the frequency of the wave. T is the time. So you can see this wave has a temporal component to it. That is to say that the displacement changes as a function of time. We then have k. K is the wave number. That's equal to 2 pi divided by the wavelength. X is the position in the x direction of this wave. So you can see that the displacement is also dependent on where along the wave you look. So you can see the wave equation takes this general form. The displacement is equal to something multiplied by cosine of the phase. And the phase is just some way of addressing our position within that wave. The phase can be anywhere from 0 degrees to 360 degrees, or we're going to use radians here, so from 0 radians to 2 pi radians. And 2 pi radians is an equivalent phase to 0 radians. You can see on the cosine graph that 0 radians has the maximum displacement, so the displacement is equal to the amplitude, and the next time that happens is just after 6. Well, that's 2 pi. On the x-axis of this graph, it looks like we have the phase in radians. Well, if theta is the phase, and 2 pi is one complete oscillation, one complete wave, then the phase is some proportion of a complete oscillation presented as an angle. So that's going to be one complete oscillation, 2 pi, multiplied by the fraction of the wave, which in this case is x, the position along the x-axis, divided by lambda, one complete wave, as measured in the x direction. Lambda is the wavelength, which is the distance in the x direction from one peak to the next. From one peak to the next is a phase difference of 360 degrees, or 2 pi radians, which I'm using here. And all I'm doing is saying that 2 pi over lambda is equal to k, where k is what we call the wave number. As wavelength increases, wave number decreases. Another way of expressing phase is as a proportion in the time dimension, the temporal dimension. So 2 pi is one full oscillation. T divided by the time period is the proportion of a wave in the time dimension. Frequency of a wave is the reciprocal of the time period. So we could write this in terms of frequency. And 2 pi f is the angular frequency, and we call that omega. So you can see we can present our phase in terms of space or in terms of time, either as a proportion of a wave in space or as a proportion of wave in time. But the waves we're interested in have a spatial and a temporal component, and so I've included both of those within this cosine. And as you can see, as time marches on, the wave appears to progress from left to right. Now I've just included another wave here, y2, which is exactly the same as y1, because my amplitude is the same, my angular frequency is the same, and my wave number is the same. So as time marches on, my blue wave and my red wave are in exactly the same place. But if I change the angular frequency to be negative, that means the wave's now moving in the opposite direction. It's still moving at the same speed though. So if I show those two waves together, I now have two waves of equal amplitude and equal frequency and equal wavelength travelling at equal speeds but in opposite directions. And I've modelled that with these two equations, y1 and y2. Now what you'll notice is that at certain times both of the waves agree, and at certain times both of the waves disagree. Now what do I mean by that? Well, remember, these waves are just a mathematical model of some physical phenomenon. So at this point in time here, the red wave and the blue wave agree. Whatever this phenomenon is, at this position here, the blue wave says go up, and the red wave says go up. So they agree. And they agree at this bottom position here, and this position here, and this position here. But at some other time, they disagree. And if you look here, whenever the blue wave says go up, the red wave says go down. Now, maybe these two phenomena are electric fields that are trying to cause an electron to oscillate. And this electron is being told go up and go down. It doesn't experience the resultant force at this instant in time. Or maybe these are two water waves that happen to meet at this particular place at this particular time, and they disagree in telling the beach ball to go up or down, so the beach ball will experience no motion up nor down. This is what we refer to as destructive interference or cancellation, whereas this, where the two waves overlap, is referred to as constructive interference or reinforcement. Now, what's interesting is what happens when we look at the resultant of these two influences. The blue influence and the red influences, when added together, produce a resultant influence. Now, I've written that equation here, y equals y1 plus y2. We're just adding together these two functions, these two wave equations. When I do that, I get this. And what you'll notice is that there are certain places where the waves never agree. So the influence, the resultant influence, is always zero. There is an amplitude of the green wave of zero at these points. Those points are called nodes. You'll also notice there are points where the waves always seem to agree, where the amplitude of this green wave is the amplitude of the red wave plus the amplitude of the blue wave. And the displacement, of course, is changing, but the amplitude is the maximum displacement. So this green wave has an amplitude on this scale of 2, because the blue wave has an amplitude of 1, and the red wave has an amplitude of 1. We add those two amplitudes together, we get the amplitude of the green wave, the resultant of these two waves added together. This point where the amplitude is at a maximum is called an antinode, and there are points all along evenly spaced between the nodes. The red wave is transmitting energy from left to right. The blue wave is transmitting energy from right to left. And so the net energy flow is zero. And that's why it's often said that stationary waves don't transfer energy. Well, they don't. They transfer energy in both directions at equal powers, equal amounts of energy per second. But clearly there's energy in this wave because we have oscillation at these antinodes and between the antinodes. Now at A level, when you look at stationary waves, that's about as far as you get. You'll look at situations where there is a node at two ends of a string and the harmonics within that node, and we can cover that later. You'll look at situations where there are antinodes at each side, or a node at one side of a piece of string and an antinode at another. But they will tend to be questions where you have the same amplitude of the two waves, the same frequency of the two waves, the same wavelength of the two waves. They're equivalent waves travelling in opposite directions. And an easy way to set that up is to have a single wave reflecting off some boundary and coming back. So the wavelength, frequency, speed of the wave that's reflected is the same as the wave that was incident on that reflecting boundary. Just for fun, I'm going to show you what happens if our two waves don't have the same amplitude. Let's just increase the amplitude of the red wave a little bit. So you can see we no longer have a stationary wave. There's a net transfer of energy from left to right. And let's look what happens if the two waves don't have the same wavelength. So let's increase the wavelength of the red wave. That means I decrease the wave number. Perhaps not that far. Now you can see the superposition of the two waves is very interesting. You wouldn't be able to set this up with reflection, because you wouldn't end up with a different wavelength wave being reflected to the one that was incident. So we can ignore that case. I also can't think of a situation where you could change the wave speed of a reflected wave. So if we change the speed of the blue wave, let's make it go faster, you can see that now there is a net transfer of energy from right to left. So that's no longer a stationary wave. Stationary waves are what happens when you get either a node at both ends or an antinode at both ends. But let's take the case of a node at both ends, and we have a wave reflecting. So in this case, remember the red wave is moving from left to right, and it reflects off the end of this string to produce a blue wave going from right to left. And you'll see when the wave reflects, its phase changes. Its phase changes by 180 degrees, or pi radians. And that means at that point where there's a reflection, we'll always have a node. We'll always have a node at the first part of the wave as well, so in the middle we have an antinode. What you're looking at here is the first harmonic, also known as the 0th overtone. The first harmonic has two nodes, one at each end, and one antinode in the middle. First harmonic, one antinode. Now here I've halved the wavelength by doubling the wave number. And what you can see now is we've got the same thing as before, a phase change at this end. The red wave moving from left to right reflects off this end and produces the blue wave moving from right to left. But now because I have halved the wavelength, we fit one complete wave along this string. We get one node in the middle, an antinode here and an antinode here. This is called the second harmonic, or the first overtone. The fundamental mode is what happens when we have half a wavelength fitting on that piece of string, and the first overtone, or the second harmonic, is what happens when we have one full wavelength fitting on that string. So here the wavelength is now a third of what it was before. It's now a third of what it was before because the wave number is now 3 times what it was before. So with a third of the wavelength, what can we see? Well, one wavelength fits 2/3 of the length of the string. We have the same phase change at the boundary where there's reflection, and we have 2 nodes and 3 antinodes. 3 antinodes, so this is the third harmonic. 2 nodes, so this is the second overtone. And now the wavelength is half of the length of the string. We get 1, 2, 3 nodes along this string, so it's a third overtone. 1, 2, 3, 4 antinodes, so it's the fourth harmonic. 1, 2, 3, 4, 5 antinodes, so it's the fifth harmonic. 1, 2, 3, 4 nodes, so this is the fourth overtone. And you can see that one wavelength now, which goes from the beginning here to the end here, is 2/5 of the length of the string. If you pause it at this point here, it becomes easier to see that that is one wavelength, 2 wavelengths, and a half. 2.5 wavelengths fits on this string. So the wavelength is 2/5 of the length of the string. And I could keep on going up, looking at these higher harmonics that fit on this string. For a harmonic to fit on the string, we have to have a node at both ends. And it's often easier to do a quick sketch and count how many nodes and antinodes to figure out what harmonic and overtone we're looking at. The term overtone isn't used as much as the term harmonic is. So that's stationary waves, and if you found that helpful, please do like the video, subscribe to my YouTube channel so you get updates when I put more videos up there. Stay safe, and I'll see you in the next video.